Hello, welcome to problem solving session for linear algebra. I am Siddhi Balgambore from IIT Gandhinagar, and today we will discuss few problems related to syllabus for week 4. That is few problems related to matrix of linear transformation, invertible linear transformations, and matrices of invertible linear transformation. And at the end, we will see a few examples of isomorphic vector spaces. So, as I said, our first topic which we will discuss today is the matrix of linear transformations. So we also saw a few questions related to matrix of linear transformation last week as well. So this week also we will start with a few questions from that section. So let us start. So consider the matrix T from beta T. So this is linear transformation matrix, and we are considering basis beta on both domain and codomain, that is domain and codomain of the linear transformation. So let me write the question. So you're considering this matrix of linear transformation, and T from P to R. So it is from space of all polynomials in one variable of degree less than or equal to 2. So such that T of Px is equal to Px plus P dash of x. So it is differentiating P with respect to x, and this linear transformation matrix is with respect to the standard basis, the ordered basis beta is equal to 1x x square. Okay, and so question is that if t beta to beta, I mean the both beta is considered as ordered basis on both domain and codomain vector spaces, and if this is the linear transformation matrix, then we need to find what is A, B, and C. Okay, so this is our question. So they have given this linear transformation T like this, and they are asking us to find this linear transformation matrix for this T, and beta is ordered basis 1x x square. So as I said last time also, so T beta 2, so for any, let me write here explicitly that for any, so let T from V to W finite dimensional vector spaces, and let beta and gamma be basis of V and W, then T beta gamma is how we write it, like the columns are coefficients of this will be T of beta 1 up to T of, suppose this is beta n, let us take both to be, and the corresponding rows are, the rows are corresponding to the gamma i's and columns are corresponding to the beta i's. So this is how the linear transformation matrix looks like. So let us start with our linear transformation. So T is P of x going is equal to Px plus P dash x. So we have, and basis is 1x x square. So we have to find first T of 1. Okay, and then again express this T of 1 in terms of beta again here, which is 1x x square. So what is T of 1? It is 1 plus 1 dash, that is differentiating 1. So it is what? 1 plus 0, which is equal to 1. And if I want to write 1 as a linear combination of 1x x square, it is 1 into 1 plus 0 into x plus 0 into x square. Okay, this is how it will be expressed as a linear combination of elements from beta. Similarly, I have to do this for x as well. So what is t of x? Is it x plus x dash, that is differentiating x. So it is x plus 1. And if I want to write this as linear combination of 1 x square, it is 1 dot x plus 1 dot x square plus 0 dot, sorry, 1 dot 1, 1 dot x plus 0 dot x square. It's okay, right? You can hear what I'm saying. Okay. And finally, for t of x square, again it is x plus x square dash, which is x plus 2x. And if I am to write this as a linear combination of 1 x square, it will be 0 dot 1 plus, oops, it is x square plus 2x. So it will be 2 dot x plus 1 dot x square. So I have all the information that I have t of all the basis elements, and I have written them in terms of the basis elements of beta again. So if I am to write this linear transformation matrix of T for with the basis with respect to basis beta on both domain and codomain, then it will be columns are coefficients of Ti's. So T beta is, so it is 1 0 0 and 1 1 0, and here it will be 0 2 1. So this is my required matrix, and I am to and I need to compare this with respect to this matrix. So, which is now this matrix. So let me, okay. So if this is the case, then just a second. Then what is A? A is, if I compare, it is 0. B is this element 1, and C is 2. So any doubt here? We were asked to find ABCs corresponding to this linear transformation matrix, and we obtained these ABCs. Any doubt? I mean, we did this kind of question last time also, but this is again a revision. So please, if you have any doubt, write it in the chat. If no, then I will proceed. Okay. Second question is similar. And again, now the linear transformation and basis are quite different. So let T from, now we are, our vector space is P3R, that is polynomials of degree 3 or less in variable x and coefficients from real numbers. T of summation ak x power k going to summation ak x plus 1 power k. Okay, this is my linear transformation, and they have not given t beta to be 1 x x square and x cube, and gamma is given 1 1 plus x 1 plus x square and 1 plus x cube, and these are two ordered bases, okay, of P3R. And they again want to find few entries of linear transformation matrix. Beta gamma, okay, and it is one 1 A21 0 A41 A12, 10, A42, A13, A23, A33, 0, A14, 0, A34, and A44. And what we want to find is, then compute. We will be following same method what we did in earlier question to obtain this, and along with just coefficient, now also they want us to find A21 plus A42 plus A13 plus A41 A14. Okay, so again now note that our beta and gammas are different, and again the linear transformation is not that trivial. They are saying that summation ak xk x power k is going to summation ak x plus 1 power k. Okay, so let me write again. So now we have beta is equal to 1x x square. So I want to compute t of 1, t of x square, and t of x cube. And I have to express them in terms of the elements from gamma. So let us write t of 1. So what is t of 1? T of 1 is, so if I want to write this t of 1 like this, so it is what? T of 1 dot x power 0. So, and it is what? 1 dot x plus 1 power 0. Okay? X plus 1. I hope you understand this, right? This t here, I'm just expressing 1 in this form, summation ak plus x power k, and it is just 1 into x power 0. And its linear transformation is going to summation ak x plus 1 power k. So again, it is 1 into x plus 1 power 0. And this is again 1. And if I want to express this as a linear transformation of gamma, so let me give this naming to this. So this is beta 1, this is beta 2, this is beta 3, this is beta 4. And let us write me like this. This is gamma 3 and gamma 4. Okay, so in that case, 1 is just 1 dot 1 plus 0 gamma 2 plus 0 gamma 3 plus 0 gamma 4, right? Because 1 is in gamma, and so 1 into 1, rest coefficients we are taking to be 0. And similarly, if I want to express t of x now, it is t of what? 1 dot x. And now it will be 1 dot x plus 1. And if I want to express this in terms of gamma, then it will be what? 0 dot gamma 1 plus 1 into 1 plus x plus 0 into gamma 3 plus 0 gamma 4. Any doubt here? I'm just expressing this in terms of gamma. So gamma is this 1 plus x, 1 plus x plus x square. Oops, here it is 1 plus x square plus x cube. Yes. Now I want to write t of x square now. It is what?
Shouldn't t of
Yes.
x be 1 plus 1 into 1 x plus 1?
Sorry, sir.
If we are doing summation.
Since I'm doing summation,
So
yes.
t of
Yeah.
x would be 1 plus 1 into x plus 1.
1 plus 1 into x plus 1. Why it would be that?
Because we are doing a summation, right? Of
But
from
for
0 to
summation, we must have two terms in the polynomial. Okay. So when we will write, okay, so let me write it explicitly. So here we have 3-degree polynomial. So how t, oh, just a second, let me write. T of, if my polynomial looks like this, a naught plus a1x plus a1 x square plus, oh, sorry, a2x square plus a3x cube, then where it goes to a naught plus a1 x plus 1 plus a2 x plus 1 square plus a3 x plus 1 cube. Okay, this is how my linear transformation is.
uh,
Here my t of 1 is what? Just if
it's
I
a
want,
single variable. Okay.
yeah, it is single variable. We are just going x plus 1 and power. Okay, I hope now it is clear, right? When I
Yeah,
write
yeah.
this. Okay, I assume that So this is okay, something which we needed. So now it is clear like what exactly I'm doing. So now x plus 1 is just 1 into x, which is going to a1 x plus 1, which is a1 is 1 in our case. And now it will be easy for you to understand what I'm doing. So t of now x square is what? T of 1 plus x square, which is 1 into x plus 1 square, which is 1 plus 2x plus x square. Now I want to express this in terms of gamma. Gamma is again what? 1 plus x, and now this time I'm not making linear equation of system of linear equation and solving. I'm just doing some smart manipulation in order to get the required linear combination. So let me write it like this: 1 plus just a second, yeah 1 plus 1 into 1 plus x plus just 1 plus x square. Okay, so I will just do this. 1 plus x square is part of my basis. And now I am remained with 1x, right? If I add and subtract 1 to this, I will get what? Minus 1 into 1 plus 1 into 1 plus x plus 1 into 1 plus x square plus 0 into my gamma 4, right? So my required coefficients are minus 1, 1, and 1. And similarly, I will do this for t of x cube, which is now t of, again, I'm writing x cube, which is 1 into x plus 1 cube. And this is what? X cube plus 3x square plus uh, 3x plus 1. And again, I will write this as 1 plus x square plus x cube. Okay, this is my one term. And now I'm left with 2x plus 2x square, right? So I'm kind of splitting this x square and x term. And if I add 2 plus minus, I do plus minus 2 to this equation. So I get this 1 plus x square plus x cube plus, now I can take 2x square and now minus 2. Okay, I did plus my, I'm subtracting here only, and let me write plus 2 minus 2. So it will be easy to understand. And what is this? This is minus 2 into 1 plus 0, 1 plus x plus 2, 1 plus x square plus 1 into 1 plus x square plus x cube. Is it okay now? I'm just kind of doing some manipulation, not manipulation, but adjusting few terms to get the required linear transformation, or sorry, linear combination. So now I have t of 1, t of x square, and t of x cube, which was my elements from beta. And I want to now express the matrix because I already wrote them in terms of linear combination of gamma i's. So then how my t beta gamma would look like? So it is this matrix: 1 0 0 0 0 1 0 0 minus 1 1 1 0 minus 2 0 1 1. Oh, sorry, minus 2 0 2 1. Okay, any doubts here? Okay, this is my required linear transformation matrix. And this is first non-trivial example which we did for linear transformation matrix. So please understand it carefully if you have any doubt. And we were supposed to find this A12, A23, A34 and this summation, this summation. Okay, so let us do that. So we, if I compared this, then A12, that is A12 position was means this, and it is 0. A23 is second row, third column, so it is 1. A34, third row, fourth is 2. And now they are asking us what is A21 plus A42 plus A13 plus A14, and now 21 is 0, 42 is 0, plus 13 is this, first row, third column, minus 1, plus again 1 4, which is first row third column, which is -2, and when it adds up it's -3. Okay, so this is what they had asked. So any doubts here, how we did, or how this manipulation, or understanding the linear transformation itself? Is there any doubt? Please understand the linear transformation is of this form. Okay, and when I do this is just a naught x power 0, and here also this is a naught x plus 1 power 0. Okay, please, if you have any doubts, unmute or write it in the chat, and let me clarify it now itself. Okay, so I assume there are no doubts. If you have any doubt, please let me know. And now this is question 3. It has a few setup. So here in third question, we have to check whether the statements are true or false. But before that, we have this setup for this question, that let V be a finite dimensional vector space of dimension n. Okay, over the field R. So our base field is set of all real numbers. And let I denote the identity transformation. Identity transformation means V goes to V. And In denotes the n cross n identity matrix. I mean, I know you know all this notation, but just a second. Assume that beta and gamma. So beta and gamma are two ordered bases of beta, of beta, of V. And we have to now check whether the following statements are true or not. Okay. So let me write this first question and first statement. It says that I of beta is I of gamma gamma. Do you understand what this is? So they are saying that if my ordered basis considered on both domain and codomain of identity transformation as beta, and this is then the required matrix of that transformation, then they are saying that I beta beta is equal to I gamma gamma. I mean, if we change the basis but keeping them same on both the domain and codomain, the corresponding linear transformation matrix is the same. That's what they are asking. So do you have any guess what this will be? Any cases? Whether it's true or false or anything, what you feel. Okay, so Jackie is saying this is true. Okay, so which is correct guess? And now even Hetvi said this is true. So now that our guess is that it's true, we need to now prove that it's true. Okay, so how it looks? So if beta, they have said that V is n-dimensional vector space, so beta will contain these n elements. Let us call them beta 1 to beta n. Okay, and identity transformation. So I want to write the identity transformation, linear transformation matrix of identity transformation. So what it is? So I of beta I is what? Beta I. And if I am to write it as linear transformation of linear combination again in terms of beta, then it is what? 0 beta 1, 0 beta I minus 1, I minus 1 plus 1 beta I, again 0 beta I plus 1, and so on up to 0 beta n, right? This will be linear combination in terms of beta. And if I want to write this, and this is true for any I between 1 to n. So if I want to write directly the linear transformation matrix, and then it will be again 1. For 1, it will be the coefficient of 1 will be 1 and rest will be 0. So it will be 1, 0, 0. Second, it will be, so coefficient of beta I. So we are talking about beta 2. So coefficient of beta 2 will be 1 and rest will be 0. So similarly like this, and it goes, and I will get rest like 1 and 0. And last will be, this is not 1 by the way. This is, now this was 1 here, and this is 1 here. Okay. So it is identity matrix. Similarly, beta was not any special, right? Even if I take basis to be gamma, then gamma 1 to gamma n, then again in that case, I of gamma I will again be gamma I, and which we can write 0 gamma 1 plus 0 gamma I minus 1 plus 1 gamma I plus 0 gamma I plus 1, and so on. I will get 0 gamma n. And corresponding to gamma again, I will get identity matrix. Okay. Or let me write directly that it will be identity matrix. So give me any basis, and if I am considering that basis on both domain and codomain, and corresponding linear transformation matrix will be identity matrix. Okay. So that's what it is saying. So what I get, that I of beta beta, this is very okay. This linear transformation matrix corresponding to beta and corresponding to gamma is actually identity matrix, and this is true for any beta, gamma, or any basis of V. So any doubts here? So this statement is true. Okay. Any doubts here, like how everything is following? If there are no doubts, if you have any doubts, please write in the chat. Or if not, then I will proceed to second part. And here now they are asking that if I take this, yeah, then they are asking whether this is identity matrix or not. So they are saying again, now it is identity transformation, but now the basis or basis of domain and codomain have changed. And they are asking that whether it is still identity matrix or not when I write the linear transformation matrix of identity transformation. And what is your guess in this case? Here we saw that this was IN. When both bases on domain and codomain were similar or same, then it was identity transformation. But now the bases have changed on domain and codomain. So what is your guess? Okay, so it should still be true. Any other guesses? Okay, everybody is saying that it is still true. Okay. Anyone who has some other guess for this? Okay, so we have identity transformation, and we have to check whether give me any two bases. If I have basis, different bases on domain and codomain, then whether it is identity transformation or not. So let me give you this. Okay, so let V be R cube. Okay, and now I have this R not R cube, R3. Okay, and let beta be its standard basis, or not beta, and B3. Let gamma, so we are starting with gamma, so it let it be 0, 0, 1, 0, and 0, 0, 1. Okay, and beta, I will just switch. I will keep the basis as a set same, but I'm just switching the order. So when we write the basis, sorry, the linear transformation matrix, we consider ordered basis. So order of the element matter in this case when we write the linear transformation matrix. Then what is I of 1, 0, 0? It is 1, 0, 0, right? And if I want to write it in terms of beta, then it is 0, 0, 1, 0 plus 1, 1, 0, 0 plus 0, 0, 1, right? 0 into 1, 0, 0, 1. Similarly, if I write this, then it will be 0, 1, 0, and it is now 1, 0, 1, 0 plus 0, 1, 0, 0 plus 0, 0, 0, 1. And third one is 0, 0, 1, and it is similar. It is 0.010 plus 1, 0, 0, 1. And I want to write its linear transformation matrix now. So I, gamma, beta. And what it is? So these were gamma i's, and these are beta i's. Okay, so these are gamma i's, and these are beta i's. So now what it will be? So this is 0, 1, 0, right? The gamma 1 is this 1, 0, 0, and corresponding to beta, the linear transformation is 0, 1. Linear combination is 0, beta 1, 1, beta 2, 0, beta 3. So it is now 0, 1, 0. Second one is 1, 0, 0, and third one is now 0, 0, 1. Now, is this identity matrix?
No.
No, it's not, right? So even though it is identity transformation, if we change the basis,
Mm.
the corresponding linear transformation matrix need not be identity matrix. Okay, so this is takeaway from this question. Is
Yeah,
it
so I
clear?
was thinking that the ordered bases are same. That's the mistake I did. Okay,
Yeah,
got it.
yeah. No, ordered basis need not be
Yeah, yeah.
same. Okay, as I said, they are same, but when we write the relay transformation matrix, we considered them as a switched. Okay, and
Mm.
even if we need not consider the basis as same. Okay, gamma could be, I can very well take beta to be this 110
Mm.
and so on. And in that case, it will be completely different matrix. Okay, we will see that in next example. So this is not identity matrix. Okay, so this statement is actually false. That if we switch the basis or if we change the basis, then it is not identity matrix, even though our transformation is identity transformation. Now, third one. Now this is, okay, no. This is I, beta, gamma, and I, gamma, beta. Okay. Now what is your guess? Now transformation is same, beta and gammas are fixed, but now we will be switching them. Okay. And what is your guess in this case? Any guesses or no guesses or only confusion? Okay, so Hetvi said that this is false. Karthikeyan is saying now this is true. Okay, so let us start writing. Okay, and we will see what we get. Okay, so in this, okay, so Karthikeyan, if you did that in this case, so what example I wrote here? If you did linear transformation for beta gamma and gamma beta for this example, and in that case you got them to be equal, and that's why you said that yes, it is true, then that does not hold always. Okay, so this is actually not true, and let us see a counter example where these matrices are different. So let our n be 2 and v be r2, and consider this beta. Okay, beta is 1 comma 0 and 0 comma 1, and gamma to be this 0 comma 1 and 2 comma 0. Okay, this is basis of r2. Okay, 0 comma 1 and uh, ordered basis of r2. Okay, and now we have to see this for linear transformation, identity linear transformation. So first we'll do for calculation for beta to gamma, that in that case what is t of 1 comma 0? It is identity transformation, so it is 1 comma 0. I want to write it in terms of what? Gammas, right? So if I want to write this in terms of gamma, then it will be 0, 0 comma 1 plus half 2 comma 0, right? This is quite clear. Okay, and this I want to write 0 comma 1, and this will be what now? 1 comma, sorry, 1 into 0 comma 1 plus 0, 2 comma 0. Is this clear? And now what my t beta gamma will be? I want to write the coefficient. It will be 2, 0, 1 by 2, 1, 0. Is there any doubt here? This is my linear transformation matrix corresponding to beta to gamma. And now I will do the other way around. Now I will do the calculation for gamma to beta. And now my basis elements of t of 0 comma 1, which is 0 comma 1. And if I want to write this as a linear combination of elements of beta, then it is 0, 1 comma 0 plus 1, 0 comma 1. And okay, this is my beta. Okay, see here. And this now t of 2 comma 0, which is again 2 comma 0, and it is what? 2 into 1 comma 0 plus 0 into 0 comma 1. And what now t gamma beta is? This is now 0, 1, 2, 0, right? And are these matrices equal? This is the same linear transformation. Beta and gamma are same, but now we have just changed their position. But the linear transformation matrix is completely different. Is this clear? But you check, if you check this for this linear transformation, which I wrote here in second example or second question, if you do that, in this case, this is the same matrix which you will get for T gamma beta, okay? But this is not true in general, okay? For this example, for we got that T from I beta gamma is not equal to I gamma beta, okay? Is there any doubt now? Karthikeyan, is it clear that this is false statement? Or anybody who has doubt in this? let me just to be clear, like therefore T is my I, okay? We are talking about identity transformation. And since this is not true for identity, this is also not true for any, this may not be true for any given linear transformation as well, okay? So I beta gamma is not equal to I gamma beta, okay? Yes, but it is purely based on basis selection, right? How can we say from the statement? Yeah, so that is, so beta, so see, what was the statement? That assume that beta and gamma are two ordered bases. Okay, so they are any ordered basis. So when I say that statement is true, it should be true for any given beta and gammas. For example, in the first question, this was holding for any given beta and gamma, right? There was no ambiguity. Even if I change beta, gamma, delta, whatever you want, give me any basis, this will always be true. Give me two different bases and this will hold. And oops, yeah. And this was in fact, if I want to write, this is in. So from same basis to same basis, if I do, then it is always identity matrix. But if I was changing even basis for identity transformation from gamma to beta and so on, it was not true. Okay, because now I changed the basis as per. Okay, so when I say a statement is true, it has to be true for any given beta and gammas. So this statement, second one, I said false because I had beta and gammas for which is what it was not true. So this statement becomes false. Okay. Third one also similarly. Okay, even if I get one pair of beta and gamma such that this statement does not hold, then it becomes false. Okay, so when we do or say true or false to general statement, if it is true, we must prove it. And if it is false, we have to give a counter example. That's how things are. Okay, so in first statement, when I said true, I gave true, I proved this, that this is what it is, that beta gamma, it will be always like this. And I even made this statement that this is not specific to beta or gamma. Give me any basis, this will always hold. Okay. And so that's how it is. When you want to say that something is false, give me an example where it is false and the statement becomes false. And if it is true, then you have to prove that it is true always, given any beta, gamma, and whatever vector space impact of n dimension. Karthik, and I hope it is clear that what I'm trying to say. Okay? Okay, clear. Okay, great. And now this next statement. Okay, you can also make few more linear transformation where, or not the linear transformation. So identity transformation is already given. So you can choose another basis and see how things look. Okay, so this is the fourth statement, that every n cross n invertible matrix, okay, can be realized as a change of basis matrix. Okay, I comma beta. Okay, they are writing I comma beta. I comma beta for some basis gamma and beta. Okay, now they are saying for some. Okay, so they are saying that every invertible matrix is a basis change matrix with respect to some gamma and beta. So when they are saying some gamma and beta, so even if I show that give me any, but in this case, it is for every invertible matrix. So give me any invertible matrix. They are saying there exists some beta and gamma for which that matrix A is a change of basis matrix. So invertible matrix is any given. Give me any invertible matrix, the statement must follow. And what is the statement? That there exists some gamma and beta for which that matrix becomes a basis change matrix. Okay. So even if I give one pair of beta gamma for which that given invertible matrix is a basis change matrix, I am through. Okay, so what is your guess now? That matrix given, that invertible matrix given is any invertible matrix, but I want to produce, or I want to say that no such beta or gamma exist. Okay, so what is your guess in this case? Or no guesses? If you have no guess, then please write that no guess. So I will understand that you are not able to guess what it is. And so I can proceed with explaining like what it is and so on. Or if you want to guess, please, no guess. Okay. Anybody who has some guess? Okay, so no guesses. So see, what they are saying that every invertible matrix can be realized as change of matrix for some basis gamma beta. So give me any invertible matrix. If I can produce some beta and gamma, I am through, right? So so my process will be that. Okay, so my assumption is that this statement is true, and since I am assuming that this statement is true, I must prove it. Okay, so proof could be anything by contradiction or constructive proof where you construct beta gammas and so on. Okay, so my guess is true, and let us start with the proof now. If I'm saying the statement is true, I must able to prove it. Okay, so our question start with say that every invertible matrix. So let us start with the invertible matrix. Okay, so let A is equal to I comma j from 1 to n, or let me just write it explicitly. It is A11, A12, A1n, and AN1, AN2, ANN, B, M, N cross N matrix. Okay, so let this be in M n cross N R. Okay, B an invertible matrix, B an invertible matrix. Okay, and I want to produce now beta and gammas such that this matrix A is their basis change matrix. When I say basis change matrix, it is I gamma to beta. So it is it is linear transformation matrix of identity transformation over the basis gamma and beta. Okay. So suppose, so when I initially thought that we will do this for Rn, but I thought that no, we should go for general statement or general proof so that there should not leave any, we should not leave any gap or so on. So I want to show that this is what we want to show, that we want to show this A is what? I gamma beta for some, okay, for some. So let me highlight this, that every for some basis, every invertible matrix, and so for some basis. So for some beta and gamma, for some basis beta and gamma of V. Okay. So let us start with beta. So let beta be E1 to En. Okay. Be ordered basis of V. Any doubts so far? I just took an invertible matrix and I'm taking any basis beta. Okay, so beta is any basis. And now what I want to give is gamma. Okay, I have chosen beta and I want to produce a gamma. Okay, so what I will do is, so A is what? A is this matrix A11, A12, A1n, A21, uh, and up to AN1, A22, A2n, AN2, and up to ANN, right? And now I take this set gamma, okay, corresponding to this column, okay. And what I do is I take this column linear combination of EIs. So what I do is A11 E1, A21 E1 E2, and so on up to AN1 EN. Okay, this is my first element of gamma. Second I do is what? A12 E1 plus A22 E2 plus A N2 En. Is there any doubt? If you have any doubt at any step, please ask, okay? A 1n E1, A 2n E2, and so on up to A NN En. Any doubts? I have just taken column linear transformation, linear combination of EIs. I had chosen beta already, and I am now correspondingly taking columns of AI as a coefficients for E1 to ENs. Okay. So if I want to name this, so this is corresponding to this element gamma 1, gamma 2, gamma 3, and gamma n. Okay. So now this is set containing n elements. Okay. So gamma has n elements corresponding to each column of A. A has n columns. So corresponding to each column, I have n many elements in gamma. And my now claim is that we claim that gamma is basis of V. Okay, right? We have taken random linear combinations. Okay, A could be any matrix, and we do not know that this is linearly independent set or not, or whether this will span or not. Okay, so one thing is that gamma has a cardinality n. Okay, so cardinality of gamma, that is the size of gamma, is n. Okay, so if I prove that it is linearly independent set, then it is enough to claim to declare that gamma is a basis of V. Is there any doubt in this statement? I am saying that gamma has n elements. So if I want to say that gamma is basis of V, it is enough to prove that gamma is linearly independent set. This is from the result from previous lectures, if you understand. Okay, so if I have dimension of V is n, then any linearly independent set of size n serves as a basis of V. Okay, so that is the statement which I will be using. Since size of gamma is n, it is enough to prove that gamma is linearly independent set. Okay. And when I want to prove that gamma is linearly independent set, what I need to start with? I have to start with linear combination. Okay. So let C1 to Cn belongs to R such that C1, let me write A11 E1, the elements of gamma. Okay. A21 E2, AN1 En plus C2, A12 E1, A22 E2 up to AN2 En and so on. I add that Cn, A1n E1, A2n E2, and so on up to ANN En. And I'm taking this linear combination to be 0. And now what I want to show that C1, C2, Cn are 0. Are you following or are you lost in between? I am producing gammas and betas for which this A will be a linear transformation matrix, where our linear transformation is identity transformation. Okay. And now what is given that beta is basis. So this E1 to EIs are linearly independent. So what I will do is I will combine the linear coefficients of EIs, and what I will get, coefficient of E1 I will put together. I will get what? C1 A11 plus C2 A12 plus up to Cn A1n, Cn A1n E1 plus now C1 A21 plus corresponding to E2. Okay, C2 A22 plus corresponding to E2, it is Cn A2n E2 and so on. C1 A n1 C2 A n2 E2, not E, A Cn A n n n is equal to 0. Okay, so I just took the linear combinations of EIs, A2, E2, and EN together, and I wrote this. And since beta is equal to E1 to En is basis, E1 to En is linearly independent set, right? So what I get that these coefficients here are zero, okay? So I will just write this is equal to zero. So this will imply what? That C1A11 plus, here I wrote C2, okay. C2A12, CNA1N is equal to 0, C1A21 plus C2A22 plus CNA2N is equal to 0, and so on. I will get that C1AN1 plus C2AN2 CNANN is equal to 0. And if I want to write this in terms of, you know, if I want to collapse and write this is what? This is just this matrix A12, A1N. Let me write this term as well. A21, AN1, A22, AN2, A2N, ANN, and this C1 to CN. And this is what? 0, 0. This is A, right? This is A. This is what our A was, right? A11, 812, A1N. This is C n cross 1 matrix, and this is now our 0 n cross 1 matrix again. 0 n cross 1. And what I want to find is, if I wanted to find what is C1 to Cn in order to prove that our gamma, which we chose, was a basis of our vector space V. And so it boiled down to finding the solution of this system of linear equation. And this is homogeneous, okay? So if at all there exists, so if C belongs to M n cross 1 R such that AC is equal to 0, okay? Then as A is invertible matrix, the A inverse exists, right? Then if I multiply this by A inverse, then I will get A inverse A, C is equal to 0, right? Oops. A inverse 0. And this is what? Again, 0 matrix. But this is what? Identity into C is equal to 0 matrix, and identity to any matrix is again same matrix. So I will get C into 0. And this is 1 cross n cross 1, okay? So if there exists any matrix C or any column vector C such that AC is 0, then that C column has to be 0, okay? So these imply what? C is 0 implies that C1 is equal to C2. That is, all the entries of this C are 0, right? So that's what we wanted. We started with the linear combination from the elements of gamma equal to 0, and we obtained that all the corresponding coefficient that C1 to Cn are 0. So this imply what? Gamma is linearly independent set, okay? And so this imply what? That gamma is basis, okay? And now if I want to write that I gamma beta, then what it is, okay? So what I of I of gamma 1 is what? Gamma 1, right? And gamma 1 is what? If I want to write this in terms of beta, then it is this A11 E1, A21 E2, A1 and En, right? A11 E1 plus A, let me just write this, A21 E2 and up to AN1 En, right? Similarly, I gamma 2 is what? Gamma 2 again, and gamma 2 was, what is it? It is A12 E1 plus A22 E2 and AN2 En, right? Any doubts here? And similarly, I of gamma n will be what? It is gamma n, and which is A1n E1. I hope I'm writing this right. No, I'm not writing this right? This will be 2. Let us see what it should be. Or no, I was writing right. A12, AN2, E2, and so on. A2n, A21, no, wait, A12. So I was writing this correct. AN2, ANN, and if I want to write this I gamma beta, then it will be what again? A11, so this should be A12. No, this was right? Yes, A21, AN1, A12, A22, AN2, and so on, A1n, A2n, ANN. And this was my matrix A. Now, is there any doubt? I know the coefficients and everything is confusing, but yes, this is our required matrix. Any doubts here? I started with, so let me go through this again. A was my matrix. I started with any ordered basis beta, and I produce this gamma. Okay, so this gamma, I proved that it is basis. And when I want to write this identity transformation with respect to gamma to beta, then the corresponding coefficients of E1 to EIs, I will write them as a columns, right? And columns is explicitly what I chose to be coefficients of gamma i's in terms of EIs. So any doubt here? Like how this is happening? Like this is not kind of very trivial, but at the same time, this is not very difficult as well. We are just following the step or the flow of what we need. I wanted this to be a linear transformation matrix. So how the linear transformation matrix is obtained? We write the coefficients as a columns of the matrix. So what I do is I choose this gamma directly as a linear combination of columns itself. Okay, or if I want to write now identity of gamma beta in front of you here, what is coefficient of E1? Okay, so this is gamma 1, right? This is gamma 1, this is gamma 2, this is gamma n. What is coefficient of gamma 1? It is A11, A21, A and 1, right? Coefficient of gamma 2, it is A12, A22, A2n. Sorry, A and 2. And this is A for last column, it will be A1n, A2n, and so on ANN. Okay. So what I did was I wanted A to be a basis change matrix. So what I did was I chose the basis obtained from the columns of matrix A. Any doubts?
Not a doubt, but the question here, if my
Mhm.
gamma had a different order basis, then also you're saying that we'll be producing the same transformation
No, 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 no,
matrix?
no, 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 no. If
No, that
gamma,
means,
for this specific gamma and for this specific beta, I am getting this. If I change even one of them, it will not be same. It will not be A. Now it will be for in some other invertible matrix. So what I'm doing is A is fixed. So corresponding to A, I am producing these betas and gammas. If I change the order of gammas, then what will happen that these columns will switch, right? If I write this second element or this second term first, if this is my gamma 1 and this is my gamma 2, okay, then if I want to write them as a coefficients in this matrix I beta gamma, then this will be my first row and this will be my second row. Sorry, this will be my first column and this will be my second column. And this is no more A, which,
but then we are
which
not showing it for every invertible matrix.
yes, we are showing it for every invertible matrix. For A, we got this. Give me any other, for example, if you give me some matrix, suppose give me B, okay? Now this B is Bij. Okay, this is my matrix B, which is Bij. Okay, and my beta is now again this E1 to En. Now my gamma will be what? This B, columns of B. What is columns of B? B11, B21, B, N1. So my gamma now is B11 E1 plus B21 E2 plus BN1 E1 En. And
So,
second element
but
will be,
then this would mean that I have to choose gamma in this way only. I can't choose any other gamma.
yes, yes, but
Okay,
what was the question? For some beta or beta and gamma. So this is my sum.
okay,
This is my chosen beta and gammas. So this is kind of constructive proof where I am explicitly giving you what is beta and gammas, what my beta and gammas are. Matrix was anything. You can choose any invertible matrix. But for that matrix, I am giving you one pair of beta and gammas for which that matrix B is invertible. So that is proving my statement, right? Matrix is any given matrix. I'm proving giving betas and gammas for every given matrix, every given invertible matrix.
okay, got it.
Yeah. Okay, got it? Great. Any doubts now? So my betas and gammas are independent of, not independent. Yeah, I mean, betas and gammas are dependent on the invertible matrix. But give me any invertible matrix, this pair of beta and gammas would work. Okay, so uh, let me just finish writing this. B21, not B12 E1 plus B22 E2 and B, what it will be, N2 E2 and so on. This will be B1, second column, yeah, last column B2N E2 and BNN EN. So for this, again, my B, if I write again now corresponding to this beta gamma, then I beta gamma, if you check gamma beta, sorry, not beta gamma, gamma beta. Gamma beta, yes. Now it is, now again, if you write, this will be A12, B2, sorry, B22, B2N2. I hope this is clear, right? Any doubts here? This beta would work. This beta and gammas would work for this invertible matrix. Okay, this invertible beta, invertible matrix. Okay, any doubts now here? That we are proving this for, understand that we are proving this for any given invertible matrix. And how we are proving it? We are giving these betas and gammas. Start from one base, any your favorite basis of that vector space V, and that gamma would be this obtained from these linear combinations of betas. And we are getting this gamma to be linearly independent set because of the fact that this B itself is an invertible matrix. Okay, so here we use the fact that A is invertible matrix. So far, for writing gamma, we need needed A to be invertible matrix. But in order to have that gamma a basis, we explicitly needed that A is an invertible matrix. Okay, and we actually use the fact that A is invertible in order to prove that gamma is linearly independent set. Okay, any doubts in this question? If you have any doubt, please write them in the chat, okay? Or you can unmute and ask. So let us move to next question. This is question 4. Okay, so this question was actually a bit time consuming, but it kind of cleared a few concepts related to the basis change matrix and how we can obtain a basis change matrix for given basis. So let V be a finite dimensional. So this is a bit light question compared to what we did just now. Okay, so and I didn't say, so this statement is actually true, okay? That we actually obtained beta and gamma such that that given linear transform given invertible matrix is basis change matrix. Okay, so now the next question, that let V be a finite dimensional vector space. Again, we are having finite dimensional vector space, and S and T be linear transformation on V. Okay, so we have to again now check which of the following are true. Okay, so my first statement is that if S and T are invertible, so when I say invertible, I mean invertible linear transformation, then I need to prove that S plus T is invertible. Not prove that, but I need to check whether if S and T are invertible, then can we say that S plus T is invertible or not? What is your guess? S and T are invertible linear transformation. We need to check or guess whether S plus T is invertible linear transformation or not. So what is your guess? Any guesses? So, I guess there are no guesses. Okay, so understand that when we have an invertible linear transformation, the corresponding matrix of linear transformation is invertible. Okay, this result is proved. Okay, so when I say that this S and T are invertible linear transformation, it means I have corresponding invertible matrices, which are their linear transformation matrices. And now I am asking that S plus T is invertible or not. Okay, so S and T are invertible, but S plus T is invertible or not. So it is like asking if I have two invertible matrices, whether their addition is invertible or not. And what is your guess in that case? If I have two matrices which are invertible, then their addition is invertible always. I'm just giving you a hint to think of linear transformations as a matrices. Okay, so if you are clear with your matrices or how the things work with matrices, then you can guess this. Or if not, then let us start with this S. So SB from V to V such that S of V is V. Okay, this is identity linear transformation, I would say. And now this t from v to v such that t of v is what? Any guesses what I would like to take this t of v to be?
S of v.
S of v?
Yeah.
No, let us take this to be minus v. I want. Okay, so this
My,
is for any given invertible linear transformations. Okay, so yeah, Karthikeyan guessed it that let us take this to be minus v. Okay, then what s plus t of v will be? S plus t of v by definition is what? S of v plus t of v. And what this is? V minus v, and it is 0. Okay, Karthikeyan guessed it. So this s plus t is giving me 0. And this is true for any v. Okay, for any v in v, s plus tv is what? 0. So this s plus t is 0 transformation. I mean, everything is going to 0. Okay. So this 0 transformation is not invertible transformation. Okay. So therefore, s plus t is not invertible. So this statement is actually false. Okay. Any doubts here? That given linear transformation, if they are invertible, our s plus t need not be invertible. And you can do this with matrices also, that if I take this identity matrix, okay, this is invertible. Similarly, this matrix is also invertible, right? But if I add them, this is completely 0, 0 matrix, and it is not invertible. In fact, this is 0 matrix. So, okay, so if you can guess this true matrices, that's also would work. Okay. And also you can, if you can't see that why this is not invertible, there is also one way of understanding this, that even if a given transformation is invertible, then it has to be injective. And the 0 transformation is not injective. That's why it is not invertible. So let us go to second. If you have any doubt, please ask. Otherwise, I will move to this next question. Let S and T, if S and T are invertible, now again S and T are my invertible linear transformation, then I want to check whether ST is invertible or not. ST is composition, okay? So ST from V to V is defined as ST of V as S of T of V, okay? This is the definition of ST of V. And what is your guess? If S and T are invertible, okay, so Karthikeyan guessed is true. Any other guesses? Anyone would like to guess what this will be, whether this will be true or false? Okay, I assume even other have the same guesses. So this is actually true. Okay, so I want to, so when we say that a linear transformation is invertible, I need to have some other. So let me write this definition. A linear transformation T from, since we are from V to V, let me write this on V to V, but we can also write this for any W. V to W is invertible if there exists a linear transformation which we actually denote as T inverse. So let me write T inverse such that T inverse is equal to identity and T inverse T is equal to identity. Okay, so that's what linear transformation being invertible means. Okay, so what we want to do is we want to obtain a linear transformation such that when I compose it with ST, I must get identity transformation. So I'm starting with ST, right? Oh, no. What is given that? T is linear transformation, right? And it is invertible. So T inverse is I mean identity transformation. And if I multiply this by S, I mean compose this on left side with S, I will get what? S I, right? This you are understanding, right? I'm composing the linear transformations. And similarly, if I compose this on left side with S inverse, what I will get? Identity. So ST and this T inverse S inverse, I'm now getting what is identity. And similarly, I can do this with S, that I can take S in or S inverse S to be identity. And again, now from this, I can take S inverse ST to be identity into T, which is T. When I say into, I mean we are composing I and T. Okay. And again, now T inverse S inverse ST. Now here I will get T inverse T, which is now identity. And what I get? T inverse ST is identity. So I'm just composing. I'm composing this T inverse with the suitable linear transformations and checking whether they are giving me identity transformations or not. Okay, so I started with the identity transformation, this T inverse. Now what I did was I composed this T inverse with T, and now again had this linear transformation, and now then I composed this with this S inverse and got the identity. Okay, and similarly I did for SS inverse and obtained that this T inverse S inverse is serving as both left and right inverse for this ST. Okay, so what we got that this ST T inverse S inverse is I and T inverse S inverse ST is again I. So when I say I mean identity transformation. So this imply what? That ST is invertible and ST inverse is in fact T inverse S inverse. Any doubts here? Any doubts, please ask. Okay, I assume no doubts. Or if you have any doubt, please unmute or write it in the chat. And now this is next. Again, we have to check whether true or false. If ST is identity, okay, identity on V. So it is identity transformation on V, then TS is also an identity or the identity transformation on V. Okay. This statement was true, by the way. Okay. This statement was true. And what is your guess on this statement? That if ST, they have said that ST is identity transformation on V. Can we say that TS? I mean, the left composition and right composition are both identity or not? What is your guess? Okay. No guess, I guess. So what we want to so they are saying that S into T is identity on V. Then we have to check whether TS is also identity transformation or V on V or not. Okay, and my guess is that yes. Okay, Jackie is saying this is false. By the way, this is true, okay, and we will prove it that this is actually true. We will obtain a inverse of TS and show that this TS is also invertible. So let us start, okay? So what is given that ST is identity on V. Identity on V means it is also, so this also implies that ST is invertible, right? And we also have one result which state that, proposition in fact, that if T from, or not T, let T from V to W be an invertible linear transformation, then T is bijection. Okay, this is we have. So what does this imply? That T, this ST is also bijection. Okay, and what we claim that now that T is also now injective map, or T is injective linear transformation. And how can we say that? When I want to say that T is injective, what does it mean? That I have to start with that T of V1 is equal to T of V2, and I have to end up getting that V1 is equal to V2. But if I compose this with ST, I get what? When I compose this T with S, what I get is this. And this implies that V1 is equal to V2 since ST is bijection or bijective linear transformation. Okay. So this implies what? That this T is injective map. But note that in our case, T is on V. Okay. So in our case, T is from V to V, right? And since T is injective map, this implies what? That nullity, null space of T is 0. This implies that nullity of T is 0. Okay, this is 0 set. And this is the number 0. Since T from V to V is linear transformation, we can apply dimension theorem. Okay, dimension theorem, if you remember, that dimension of V is nullity of T plus rank of T. And this implies what? That dimension of V is equal to rank of T, and which is n. And once I have rank of T as n, I get that T is also surjective map, because we know that image of a linear transformation is a subspace of a codomain. Sorry, okay. Okay, so Paras session recording will be uploaded by maybe 7 p.m. today. Okay, you can check the YouTube links on the same channel. It will be uploaded. Okay. And for this, the T to be surjective. So T is surjective. Sorry. So T from V to V is linear transformation, and we applied the rank nullity, and we got the T surjective. So what I was saying that since rank or the image space or the range of T is a subspace of our V, and rank of T is n, implies what? That range space has dimension n. And we know that if a subspace of a finite dimensional vector space has dimension equal to the dimension of V, then that V is equal to W. So this is also proposition from previous lectures. Okay, so this implies that T is surjective, and therefore T is bijective now. And once again a proposition is proved, and it states that if T is a bijective linear transformation, then it is invertible. Okay. And this will give me what? That T is invertible. Okay. So this is not very trivial to think of this way. And why only T? Why not S? And so on. But this is how it is. So we now have the information that T is invertible. What I want to claim is that TS is invertible. Oh, sorry, TS is identity. Okay, so I want to start proving this. So let us start with ST. Okay, so we are given that ST is identity. And now what I will do is I will pre-multiply. I mean, I will compose this ST with a T and I will get T, right? T into I, which is T. Now T is invertible, right? So T inverse exists. So now we can post multiply this by T inverse. So what I get? T inverse, which is now again I. So, and if I separate this is correct, right? TS into I, and this is I. TT inverse is now I. So I get TS is equal to identity. And this we could do because since T is invertible, okay? So we explicitly prove that T is invertible and that's why we could multiply this by T inverse, okay? So any doubt here that ST is I? So we got that TS is I. And in order to get that, we proved that T is invertible linear transformation. So this is also true, okay? So if ST is identity, we can very well say that T is invertible. But the fact that here T, ST and everything is from same vector space to same vector space. So ST and everything is from V to V here. Now fourth question is that any doubts here, please ask. I mean, I know these exercises are not very trivial and in fact they are bit technical and expecting a lot of results from previous lectures. So, but that's how we will learn. Okay, so let us start with next question. So this statement was true that we got TS is also identity. So now what we are given that S and T, ST are invertible, then T is invertible. And what is your guess in this case? Any guesses? Okay, so we saw so many things about invertible. So, and what is your guess now that S and ST are invertible? So whether T will be invertible or not? So let us start. Okay, given that ST is invertible, so what does this mean? That ST and ST inverse exist and we can write this to be I. Okay, it is invertible. Okay, so Karthik can guess that T is invertible and the guess is true. And I mean, the guess is correct. So let us start. We have this information. Okay, ST is S inverse T inverse. And note that when I'm writing this, I'm not writing this as T inverse S inverse. I'm saying that ST is invertible. So there exists a linear transformation which serves as inverse of ST. And I'm calling that as ST inverse. And this is not S inverse T inverse in general when I am writing this. I mean, at this moment, it is not. Okay. So I can multiply this. So, okay. So I can write this as ST inverse I. And now what I do is I pre-multiply this by ST inverse. So oh, S inverse ST inverse. Since I can do this because since S is invertible, okay? And this will get what T? ST inverse is equal to S inverse. And now what I will do, I want this to be identity, the right hand side. So what I will do is I will multiply this with S. I mean compose this with S and we will get what? This T, ST inverse S is equal to identity. Okay, I got that. So this is some linear transformation such that I got T. When I compose with this linear transformation, this new linear transformation, I get identity. And from third part, which we proved just now, that what I say that if ST is identity, then TS is also identity transformation, right? So what I had here that TS is identity. So by part 3 of this question, what I get that ST inverse S T is also identity, right? I'm just using the previous part. If you don't want to use that previous part, you can just switch this ST. You can start with ST inverse T and you will get that this again element into T will be identity. So this implies that T is invertible because I obtained a linear transformation such that when I compose it with the T on left and right, I get the identity transformation. Okay, so this statement is actually true. Okay, any doubts here? Anyone who has not said anything, any doubts? Okay, if you have any doubt, please stop and ask. And please unmute yourself and ask or write it in the chat. On this, oops, this is last of this part, that they are now asking that there does not exist any, there does not exist S from V to V and T from V to V such that ST is 0, ST is 0, but TS is non-zero. Now they are saying that it does not exist. So if I want to prove that this does not exist, I want to show that no such S and T are possible for which ST and TS will be 0 for any given STs. But if I want to say that this is not true, it is sufficient to give me just one example for which we have S and T from V to V such that ST is 0 but TS is non-zero. So what is your guess? Whether this is true or not? I mean, there exists or there does not exist. Any guesses? Okay, so my guess is, so this statement is false. I mean, we can show, so let V be R2, okay? And T from V to V, we define T to be T of x comma y going to x comma x, okay? And S from V to V, we define this to be Ts of S of x comma y, we define and x minus y, x minus y. Okay, these are linear transformations. Is there any doubt that this is not linear transformation or anything of that kind, you can check that these are linear transformations. Okay. And now if I take st of x comma y, what it will be? It will be s of t of x comma y. And what is t of x comma y? It is x comma x, right? And when I apply x s on this, it is x minus x, x minus x. And what this is? This is 0 comma 0. And this is true for any x comma y in R2. This holds. Okay. So this imply what? That this st is 0. I mean, this is 0 transformation. But what is ts? Ts of x comma y is t of s of x comma y. And what is s of x comma y? It is x minus y comma x minus y. And what is t of x comma y minus? It is just first coordinate repeating itself, which is x minus y here. Okay. And this is not a 0 transformation, because explicitly if I take ts of, let me take 2 comma 0, then it is what? T of s of, this is 2 minus 0, 2 minus 0 from, I'm just copying this from here. And this is 2 comma 2. And this is non-zero. So this ts is non-zero linear transformation. Okay. Any doubts? So this is the example where st is 0 but ts is non-zero. However, if st was identity, we proved that ts was identity. But for 0 transformation, this is not the case. Any doubts here? So this statement is actually false. There does exist. And we just explicitly showed that this is the example of v, s, and t's such that st is 0 but ts is non-zero. Any doubts? Or is there any doubt understanding the linear transformation? You can check that this is linear transformation, okay? You can check this.
Remove the, does not remove, madam. There existed, that is true or false, no?
That does not exist. So if I
No, madam. Remove does not, madam. There exists S V22 and T V2V such that ST is equal 0, but TS is equal 0. That statement is true or false, no?
yeah, but this statement also holds. So if I'm to write no, if I remove the not,
Does not remove.
So if I remove not, then this statement becomes true. There does exist. So this statement becomes true. The statement is now that there does not exist. So it is false because there exists. Okay, so
But
if
my
it is
doubt is,
confused,
my
so
doubt
if
is
I
does
remove
not
this not, the statement becomes there does exist S and V such
does
that
also
TS is
remove, madam. Does also remove.
okay. Okay.
There exists S2 V2 V2V, T is V2V.
Okay.
So this statement,
So in
I
that
want
case,
this
the
statement
statement becomes true.
true.
Yeah.
Yeah, thank you. That is my
Yeah.
doubt.
Yeah. Okay.
Yes, madam. Thank you.
Yeah, sure. So if we keep the statement like this, and if this is less confusing, then let us keep it like this. Thank you, sir. Okay, so this is true because we showed that this exists. Any doubts here? Any doubt, please? If
Madam, the
not,
statement
then
given, there does not given the statement, that statement is false.
yes, yes. If it asks that there does not exist, then it's false because we showed that there exists a pair of S and T. But if
Yeah,
they are asking that there exists, then it is true because again we have an example. They are
yeah,
just asking about existence. So
yes,
yes,
okay. Yeah, thank you, ma'am.
and yeah, sure. So this is now next question, or this is the last question. We have few minutes, so we can very well do this. So let us start with this question, and here we just have to check that which of the following pair of vector spaces are isomorphic or yeah, are isomorphic or isomorphism. Okay. So before we move to this question, there is one proposition proved in the lectures that it said that let V and W be finite dimensional vector spaces. So when I say isomorphism, I mean the bijective linear transformation. Okay. So they're saying that we have V and W are vector spaces. Then we say that V and W are isomorphic if and only if dimension of V is equal to dimension of W. Okay. And this is what we will be using in the next examples. So let my V1 be R4 and V2 be P4R. So this is P4R means polynomials with degree less or equal 4. Okay. 4. First dimension of V1, that is dimension of R4 is what? Dimension of R4 is, it is 4. That's what we know. And now we have to check the dimension of P4R. Okay. And what is it? So one of the bases which we know of P4R, so let me write here P4R to avoid the confusion. It is this, right? 1x, x square, x cube, and x power 4. So what is cardinality of this? It is 5, right? So here dimension of R4 is actually not equal to dimension of P4R. So from this proposition, we can say that R4 is not isomorphic to P4R. And when I say that these two are not isomorphic, yes, Karthikeyan said that dimension of P4R is 5. Okay, so when I say that R4 is not isomorphic to P4R, I mean there does not exist any bijective linear transformation from P4R to R4. Okay, this is what it means, that there does not exist. Okay, so I hope there was no doubt here. We just to say that these two are isomorphic or not. Since there are all finite dimensional vector spaces, we just have to check whether they have equal dimension or not. And in this case, since the dimension was not equal, we got that R4 is not equal to R4 is not isomorphic to P4R. So now our V is subset of M2R such that trace of A is 0 and W is R3. Okay. So since we know dimension of W or dimension of R3 is 3. And now we want to check what is dimension of V now. So what is V? Let me write explicitly. So what is V? If A, B, C, D, if this is in M2R, then when I say trace A is 0, it means what? A plus D is 0, right? I want A plus D to be 0. And what does this mean? That A, B, C, D belongs to M2R such that D is what now? Minus A. So if I substitute this just here, I get that it is A 1 0 0 minus 1 plus B 0 1 0 0 plus C 0 0 1 0 such that A, B, C in R. Okay. So what does this imply? The dimension of V is, yes, Jackie said that it's 3. Okay, so dimension of V is now 3. So now what I have, the dimension of V is dimension of W, right? Both of them is 3. So that's why this R3 is actually isomorphic to a subspace of M2R, which is set of all matrices with the trace 0. Okay, so these two spaces are isomorphic. So what does this imply? That there exists a bijective linear transformation or isomorphism or invertible transformation from V to W. Okay. Now let us move to third question. Third question means again the third of this kind. R6 and M2 cross 3R. Okay. So R6 again, dimension of R6 is 6. But what is dimension of M2 cross 3R? Any doubts? I mean, any guess? What is dimension of? Let me write this M2 cross 3. R. How does this look like? This is matrices of this kind. A, B, C, D, E, F belongs to M2 cross 3. 2 rows and 3 columns. Okay. Such that this A, B, C, D, E, F in R. Okay. I mean, this was not needed, but okay. So what is, if I want to split this, this is A 1 0 0 0 0 0 plus B 0 1 0 0 0 0 plus C 0 0 1 0 0 0 plus D and so on for all the entries, and such that what this A, B, C, D, E, F are from R. Okay, and then what I get, the dimension of M2 cross 3R is what? 6. Okay, Karthik can guess that it is 6. In general, for any M cross N matrices, if I express this for, so if I consider this M cross N R, and if this Eij is some M cross N matrix such that everything is 0, okay, this only this ijth entry. So let me write this ijth entry is equal to 1, rest all entries to be 0. This always serves as my basis of Mn cross n R. Okay. And there are how many possibilities for this? M into n possibilities, right? Since M into n, each entry I can choose from R. So this beta Eij 1 less than equal to I less than equal to M and 1 less than equal to J less than equal to N will always serve as a basis of M cross N R. Okay. And this is M cross N matrix. So dimension of any n cross n matrices is always m into n. Okay. So here the dimension of this M3R is a 6. So therefore dimension of R6 is equal to dimension of M23R. So this implies what? That R6 is isomorphic to M2 cross 3R. Any doubts here? And also for here, that how the dimension of any M cross n matrices is M into n.
Hello.
Yes, Ramya.
One of our dimension, ma'am. How to
Sorry?
find Mn of R, polynomial Mn of R.
Yes, I'm coming to that. Polynomial mn. So polynomials of degree mn, right? That's what you are asking.
And
Yes, I will come
also
to that.
R power Mn.
Yes, I understood that. So let us go. Yeah, so next question is related to that only. So let us write this. The fourth question, where V1 is m cross n r and V2 is this p m n r. This is what you are asking, right, Ramya? Dimension of this.
Yes, ma'am.
Yes, right? So let us see this. So as I explained earlier, dimension of MMNR is what? I just explained. Please somebody write in the chat or say it out loud. MN. Okay, so Jackie said that it is MN. We just saw that dimension of MNR is M cross NR is MN. Okay, Ayushi also said that it is MN. So now we have to check. So even Ramya asked, we have to now see for dimension of PMNR. So how the elements of PMNR look, right? So if P belongs to this PMNR, it means that P is of this form, right? A0 plus A1x, so on up to AMN x power Mn. So it is of degree Mn. So it is Mn degree polynomial. Okay, polynomial of degree Mn. So how many? So if I am to write this explicitly, so it is what PMNR will be A0 plus A1x plus AMN x power Mn such that this A0, A1 up to AMN, Mn are in R. Okay, so this is, and how many elements are here which are independent? These are Mn plus this one, right? So dimension of PMNR is Mn plus 1. Any doubts? Yes, even Karthikeyan guessed that it is Mn plus 1. Okay, so in general, dimension of PNR is n plus 1. Okay, and you can always choose this basis. Beta is equal to 1, x power n. And cardinality of beta is here n plus 1. Okay. So instead of mn, even I had to write it here mn plus 1. It will be mn plus 1 plus 1. So it will be mn plus 2. So dimension of PMNR is mn plus 1. Any doubts, Ramya? You got this? That dimension of PMNR is mn plus 1.
Thank you, madam. Very nice explanation.
Sorry?
Thank you, ma'am.
Okay, thank you. Okay, great. You understood, I mean. So here what we got, the dimension of V1, that is dimension of M cross, it was M cross N matrix, okay. It was M cross N, R was what? Mn, but dimension of our V2, which was dimension of with MNR is Mn plus 1, right? So what we get here, that dimension of V1 is not equal to dimension of V2, and therefore by the proposition which I just mentioned earlier, that M cross N R is not, the matrices of order M cross N is not isomorphic to P, M, N, R. Okay, there does not exist any linear transformation which is bijective or invertible such that from MNR, MMNR to PMNR. Okay, this is polynomial of degree Mn, and here they are M cross N matrices. And this is one more. So our V is now A in again M2 cross 2R. So we are now back to M2 cross 2 such that A is equal to A transpose. This is our V, and W is what? A in M2 cross 2R such that A is minus of A transpose. And what is your guess? Whether they are isomorphic or not? Okay, so what is your guess? These two are isomorphic or not isomorphic? I know we need to find dimension and so on, but by looking at them, what is your guess? Whether they are or they are not? Okay, so there are few guesses. So let us check what is their dimensions. Okay, so Karthikeyan said that yes, they are isomorphic, but let us start. So what is V? It is, we are starting with A in M2 cross 2 matrices, so it is ABC. So let this be M2 cross 2 are such that A transpose is equal to A. Okay, so what does this mean? A, B, C, D is equal to now A transpose. So what is A transpose? A, C, B, D, right? This is D. And from here, what we get, this imply what? So this will imply what? That A is equal to A is fine. But what this implies that B is equal to C and rest A, comma D are in R, right? So what I get here, or let me write C is equal to B, and A and D are in R. So what I get, that this is A. Now C is B is here, but like this in M2R such that A, B, D in R. So if this is confusing, this is of the form 1, 0, 0, 0 plus B 0, 1, 0 plus D 0, 0, 0, 1 such that A, B, D in R. And now what is the dimension of V then? It is 3. Okay, we have 3 elements which is producing this vector space. And now what is W? W is again A, B, C, D in M2 cross 2R such that now what I have? A, B, C, D is equal to what? Minus of A transpose. So minus of A, minus of B, minus of C, minus of D, right? And what does this imply? That A is equal to minus A, and so this will imply that A is 0, right? Oops. This has to be C and D transpose and then subtracting minus this B. So what this is imply that B is equal to minus C is equal to minus B. And this imply what? These two statements imply what? C is equal to minus B, right? And last one is what? D is equal to minus D, and this will imply that D is equal to 0. So the elements are of the form what? A is 0, D is 0, C is equal to minus B, and here B belong to M2 cross 2 R. And this B is in R. And if I want to write this explicitly again, it is B into 0, 1, minus 1, 0 in M2R such that B in R. So what is dimension of W now? 1. Okay, Ayushi said the dimension of W is now 1. So therefore, dimension of V is 3 and dimension of W is 1. Therefore, dimension of V is not equal to dimension of W. Okay, and what we get is that V is not isomorphic to W. Okay, so these two are vector subspaces of M2 cross 2R. Okay, but these two vector subspaces are not isomorphic to each other. Okay, and we obtained that using again that proposition which said that two vector spaces are isomorphic only if their dimension is equal. Okay, so any doubt here? No doubts. Great. So this was the theorem to remember for this question, that two vector spaces are isomorphic if and only if they have same dimension. Okay, so I think we are over with the time, so we can stop here. But I hope there are no questions in the whatever we did today so far. And if there is a doubt in this question where we proved that for this question, I guess this question was a bit difficult. So you can just go through the notes again, and or for the video link will be available by tonight. Please go through that, and if you have any doubt, please ask in the discussion forum, and so on. So this is it for this week's problem solving session. If you have any doubt, please ask. Otherwise, we can wait. So if you have any doubt, please write it in the chat box or unmute. Or if there is any question where you couldn't understand anything, please ask. Or if you have any doubt from the lectures as well. Okay, so no doubt. So we will stop for today then. Okay, thank you. And we will meet again next week, same time, Saturday, 3 p.m. If you have any doubt, please write in the discussion forum. So we are closing this session for now. Thank you.
Thank you, ma'am.
So thank you.